Wow, two people with the same template.
Good evening, everyone. My name is Dhawan, and these are my team members, Behnaz, Brian Luke, and Ehsan Foroudi. We're here to present our senior design project, Behavioral Algorithm Sensor Suite, better known as Behnaz. So today we're going to go over the problem statement, the top-level design that we use to solve our problem, components for our solution, and supporting material. Right. As we all know, the numerous professions work with robotic systems. They might be scientists or enthusiasts. But some professions, such as computer science, do not include formal training in hardware. So in order to target this field, what we did is we created the hardware and a configurable software suite for this purpose. So we built up a configurable sensor ring, the necessary software required, as well as a drive platform to demonstrate the usefulness of our system. This is our top-level design. As you can see, it's highly modular. On top, we have a high-level controller that communicates with our sensor control and our drivetrain control. The sensor control gets an information from the ultrasound and the infrared sensors, and the drivetrain control gives motor output to the motors and gets odometry information from a PS2 mouse that we have at the bottom of our robot. For a high-level controller, we're using the gumsticks. The gumsticks uses an ARM processor. It runs at 400 megahertz and has 64 MB of RAM. You might ask us why we're using such a powerful processor. Because it has that much memory, we can put a lot of behaviors into it, and it also runs Linux, and people in robotics field love using Linux. For our sensors, we're using the RoboSticks. The RoboSticks has over 40 GPIO pins, which help us, we can add a lot of sensors onto it, and it also serves as a base for our gumsticks. The Arduino we primarily use because to speed up development, and it was a good platform to test our drivetrain. Now I'm going to let Isaac talk about the drivetrain.
As you see, this is the top-level design of our drivetrain. This drivetrain is being supplied by 14.4 volt power supply, being voltage regulated, dual voltage regulated by 8 volt and 5 volt. The 8 volt would supply our DC motors, and 5 volt would supply the logic. The H-bridge and DC motors, as you see, is connected, and we have the control logic, and we have the Arduino. The 5 volt will supply the logic itself, and the microcontroller will control the optical encoder, H-bridge, and our DC motors. Now, originally, our idea was using a Lego platform, but it was not successful due to the weakness of the structure, and we had so many mechanical problems. So we had to purchase a modular metal platform, which in case still we did a lot of modification on that platform itself, consisting of our H-bridge. First of all, we blown out the first H-bridge. We had to buy another one. It was expensive. We had to wait for the shipping, so we said we have to make our own H-bridge. It wasn't that complicated. 754410 is the H-bridge chip that we used, plus the logic gates, NOT gate and AND gate. Then, as far as the wheel goes, the wheels, we had to go back to our previous Lego wheels. They had better grips, and they worked well. And also, as far as our caster wheel go, we actually had a good idea of returning that caster wheel into our steering wheel. So we got a servo motor connected to the caster wheel, and it helped us a lot with corrective action inside the mix. Now, Behnaz is going to cover this sensor.
So we've just talked about the legs of our robot. Now we're going to talk about the eyes of our robot. The sensor ring had two dimensions to it, an electrical and a mechanical and a software. Now, the mechanical part was the very first part. We designed the initial prototype of the ring using AutoCAD. And the reason why we did this is because the different sensors that we utilized, both ultrasound and infrared, had different parameters on where they had to be placed. And as a matter of fact, if the infrared sensors were placed in the wrong place, they'd give you erroneous data, which is unacceptable. So what we did is we gave the ability to have up to 8 ultrasound sensors and up to 8 infrared sensors. The infrared sensors allow you to get good resolution at low crosstalk, and the ultrasound sensors allow you to get long distances and are inherently linear. As you can see here, we went from a prototype to a final design for the metal. We started out with the AutoCAD prototype and finally built it in metal using machining techniques. In addition, we also created a PCB to interface the sensors. Here's a PCB design schematic, and here's the final implementation with partial population. Now, the rest of the actual function of the sensor ring was accomplished using C and a microcontroller, the Admiral 18MEGA128 on the Road 6. What we did is we used an operating system called FreeRTOS. And what FreeRTOS does is essentially allows you to make a platform-independent set of tasks. So what I did is I broke it down. I said ultrasonic range-finding task, handling the controlling, the firing, and the processing of the ultrasound, the infrared range-finding task, handling those tasks, as well as a fail-safe task. In case any of the sensors failed for whatever reason, power or something, it would prevent the entire system from going down. And also there's a communications task to take the data, process it, and send it up to the higher level controller. And to verify this, we used the LabVIEW graphics program. What we did is we took a look, if you see here, up in the upper right here side, we have a polar plot of what the sensors are seeing. So instead of just seeing data packets and trying to debug like that, what we did is we allowed ourselves to get a visualization of what the actual obstacles that the sensors were seeing. So in this particular case, we have the ultrasound sensors lined up against an array of obstacles. So you can see here the obstacles obviously range a lot shorter distance than the free open space. And I'm going to introduce Mr. Luke.
So we have a sensor ring and a drive system. We needed some system higher order controller to control it. We accomplished that in 2 parts, our robot algorithm core, our RAC, and our robot configuration application. And overall, all of this combined to over 7,000 lines of source code.